So the thing I want to talk about today is something called a gauge theory. Now, everyone talks about, if you heard physics conversations, you might have heard the word gauge invariance, gauge theory, gauge symmetry being used, and it's kind of a bouncer because we haven't been introduced to these things in undergraduate physics. So, what a gauge theory basically means. Okay, so let's take the equations of motion. Now, if I were to drop a ball, um, if I were to drop a ball from here to this table, the velocity, at this point would be given by the equation v equals root 2gh. Well, what is h? I'm defining h with respect to this. The table is the baseline where h is 0, and if I raise it to over here, it will be about a foot. So that is the root 2gh, and the h depends on the table over here. Now if I drop it, we can calculate the velocity based on the h from here. Now if I move this apparatus, let's say to the ground floor, I'm on the first floor, or to the floor over here, to the floor instead of this table, if I keep that as the baseline, and if I drop the ball from 1 foot over there, the velocity will not change. So if it's 1 foot above this table or 1 foot above the floor, the velocity will not change. So because the equations are invariant, this is gauge invariance. So if you change the background, you're not changing the equations, the physics will stay the same. So that is what we mean by gauge invariance. And why this funny term gauge? Well, apparently there's a legend that maybe some mathematicians or physicists were looking at railway tracks, and you have these gauges which hold the tracks in place, and they look the same. And apparently that was how the term gauge invariance was coined. So now we've talked about gauge invariance in terms of gravity. So what do we mean, uh, when we talk about gauge invariance in stuff like field theories, quantum field theories, and you know wave mechanics? So if we were to imagine a wave function, okay, let's forget the wave function. First, let's talk about an ordinary wave. Let's say I have a wave which is moving in space. It is given by the standard formula, um, a into sine kx minus omega t. That is my wave. So now if I were to shift this wave a little to the right in space, I would introduce one more term called phi. Phi is the phase angle, and that would change the phase of the wave. So if I'm moving the wave a little bit to the right, I'm changing the phase of the wave. Now will it change the equation? Yes, it will. I'm adding a phi term. Now if I were to move the universe behind the wave, if I were to keep the wave over there, I've moved the wave by phi. If I were to move the universe behind also by phi, the physics of the wave would stay the same. This is gauge invariance in terms of wave mechanics. So all the big theories we know about, be it Newtonian gravity, be it Einstein's theory of gravity, Einstein's field equations in general relativity, be it the Standard Model Lagrangian, which talks about particle physics, or Maxwell's theory of electromagnetism, all of these are gauge invariant. So that's just something which pops up in physics. All of these good theories turn out turn out to be gauge invariant. Now, when we talk about the Schrodinger equation, the Schrodinger equation has the Born normalization condition, which talks about psi and psi star, which is the complex conjugate, which is psi star, and the psi. When you normalize them, when you multiply psi star into psi, only then it starts making sense, because you can't measure complex wave functions. It doesn't make sense. So you can only measure the square of the wave function, which is the probability density. So the square of the mod of psi, and when you multiply these conjugates, you get something which is workable. Now if I were to move the wave function by a phase phi, do I change anything? Well, if the equation is defined in terms of position, and if I change the whole equation by a phase phi, this is called global invariance. So I'm changing the whole equation, the whole function, the whole wave function is moving to the left or right by phi, and this will not change anything. This is going to stay the same. It's and because I'm changing the whole thing, it's not going to change, and it's called global invariance. Now if I change only a small part of the wave function left or right, it's going to mess up our equation, and this is called local invariance. So local invariance and global invariance are different things. And I guess this should be it for today's video. We can talk about quantum electrodynamics and Yang-Mills theory in future videos. So I guess this was intuitive enough to bring the idea of gauge and gauge symmetry to an understandable level. Thank you for watching.